quantum mechanics. To begin with, what do you understand about quantum mechanics?
Hi Li-Ting, good question. Not much actually. Basically, quantum mechanics is predicting future behaviors of quantum particles such as photons and electrons. To predict where the quantum particle will be in the future, we just plug the wave function into Schrödinger wave equation, the quantum equivalent of Newton's law of motion F equals ma.
A wave function in quantum physics is defined to be a function describing the probability of a particle's quantum state as a function of spin, time, momentum, and position. Based on the Copernican interpretation, subatomic particles are described by a wave function, and this wave function obeys the Schrödinger equation until measurement is made.
Wave function on its own is probability amplitude with no physical meaning. Max Born formulated the interpretation of wave function or psi, which is the square of the absolute value of wave function, gives physical meaning, which represents the probability of finding a particle in any one particular state if we were to measure it. This means we can extract the position of a particle or other measurable physical quantities from this wave function by doing different mathematical operations on the wave function for each property we want to find.
There are many possibilities of wave function, which they just have to satisfy a set of constraints. Firstly, a wave function must be a solution of the Schrödinger equation. Secondly, when we calculate a probability from the wave function, we will get a probability distribution, and the area of this needs to be equal to 1. Technically, we say that the wave function must be normalizable.
The wave function model predicts what subatomic particles will do incredibly well. But weirdly, we've got no idea if this wave function is literally real or not. No one has ever seen a quantum wave because whenever we measure an electron, all we ever see is a point-like electron particle.
The subatomic particle is simultaneously everywhere the wave function says it can be. And then, when the particle is detected, the wave function collects, which we know with 100% certainty where the subatomic particle is. It is to say that the measurement collects the wave function. The inability to observe such a collapse is known as the measurement problem and has given rise to different interpretations of quantum mechanics.
The famous double slit experiment demonstrated the particle wave duality of the particles. If we only detect the electrons at the second wall, we see wave behavior. If we detect electrons at both walls, we see particle behavior. This is not only true for electrons, but for everything in the universe.
The consequence of these wave functions are the quantum phenomena. One of these phenomena is the Heisenberg uncertainty principle, which says that we can never know the exact position and momentum of an object. This is the fundamental property of the universe. The position is given by the amplitude of the wave, and the momentum is given by the wavelength of the wave. In this principle, we can only know certain things precisely, but not everything. Either we have a definite value of momentum and don't know anything about position, or we know the position very well, but don't know anything about the momentum, or we are in intermediate state.
The other phenomenon is the superposition, where a particle lives in both the spin up and spin down state at the same time, but once the particle is measured, it has to take on one of the two states. In quantum mechanics, if we have two or more wave functions that have valid solutions of the Schrödinger's equation, then any combination of these wave functions is also a valid solution. This is where the Schrödinger's cat thought experiment comes from.
The next strange phenomenon is quantum entanglement. two subatomic particles entangled in a superposition state, where if one spins one way, then the other must spin the other way. Even there's no way for information to pass from one particle to the another.
Now onto the quantum tunneling. Quantum tunneling is where particles have a probability of moving through barriers. Even the particle doesn't have enough kinetic energy to overcome the potential barrier, sometimes it can end up on the other side. This can be done because of its wave function.
The standard interpretation is Copernican interpretation devised by Niels Bohr and Werner Heisenberg, which treats wave function collapse as a fundamental process without explaining the details of how it happens. According to interpretation, the quantum world is governed by a set of probabilities and is described by a wave function that evolves over time in the Schrödinger equation. Prior to this observation or measurement, the microscopic world exists in a state of all possible paths at once. The act of measuring force the set of probabilities to randomly assume one possible value. It is what we call non-deterministic interpretation because there's no underlying predictability behind the selection.
Owen Schrödinger found this ridiculous, and he proposed his famous Schrödinger's cat thought experiment to highlight the absurdity. Because the existence of a cat that is both dead and alive at the same time is absurd and does not happen in the real world. This thought experiment illustrates the weirdness of Copernican interpretation. The issue is the rules of quantum world cannot be applied to macroscopic objects.
The many worlds interpretation of quantum physics postulated by Hugh Everett, on the other hand, says that the universal wave function is objectively real, and that there is no wave function collapse. This implies that all possible outcomes of quantum measurements are physically realized in some world or universe. It postulates that the world splits every time quantum states diverge in two different probabilities due to a quantum measurement. For example, if we were trying to measure the spin state of an electron, the many worlds interpretation says that the measuring device becomes entangled with the electron. This causes something called decoherence. The decoherence splits the universe into two due to the mutually exclusive results, such that with one universe, the device measures spin up, and in the second universe, the device measures spin down. The problem of this interpretation is no connection between the world exists, so it is unclear whether we could ever verify whether the other world exists.
Okay, thank you Li Ting for the discussion. Now I think the more I know, the more I confuse.
Alright, thank you to Angelina. Me too feeling confused, but now for one fact. If you aren't confused by quantum mechanics, you haven't really understood it.